In the last few weeks, we've spent a lot of time building up a basis of logical symbols and how we can manipulate them to prove interesting things about mathematics. This week, we will complete this task by adding in universal and existential quantifiers and discussing how they can be proved and how their negations can be proved. The last step in building our set theory knowledge is understanding big union, intersection, and product notation. We will cover all those in the next video. To start, we want to ask ourselves the question of how can we talk about general things in mathematics? These will often come in two flavors. Either we would say that something with a certain property exists, or that all things satisfying a hypothesis will satisfy a given property. And the key words that I want you to notice here are there exists and for all. So some examples include this. So there's a carrot whose color is not orange. So here I have a yellow carrot that I found on Google Images. Another example is for every planet in the solar system farther to the sun than Venus, there is at least one moon associated to that planet. So this here is some information that I got from NASA. As you can see, every planet after Venus has at least one moon. Perhaps a more mathematical context is the following, which states that there exists a number such that no polynomial with rational coefficients contains it as a zero. So what does that mean? Well, remember that a polynomial, p, is usually of the form an x to the n plus an minus 1 x to the n minus 1 all the way up until a1x plus a0, where all the a's are like real numbers and x is just some variable. Okay? So if my a's are not just real, but I require them to be rational numbers, so fractions, there are actually numbers which never appear as the root of these polynomials. And they are often called the transcendental numbers. You know a transcendental number. One example is pi. There's also e, which is Euler's number. But there are many, many more transcendental numbers, and we will discuss more of those later on. Another really easy example is the fundamental theorem of arithmetic, which I've abbreviated to FTA. This is just the statement that every natural number can be uniquely decomposed as a product of primes. So here are some other more complicated examples, and we will prove next week that the size of Z as a set is in some sense smaller than the size of R, the real numbers. And a question that sort of comes from this discussion is another existence question. Does there exist a set whose size is in between Z's and R's? So if we were to naively think about them as like sets, right? We would say maybe this is Z, and we're going to learn that Z is smaller than R. And so the question is there maybe a set whose size is in between Z and R's, right? Now, the answer to this question may be yes, it may be no. Our finite intuition doesn't actually tell us anything. For example, let's say I have a set with 3 elements, right? And I have a set with 4 elements, right? So this is one set, this is another set. Clearly, this set has less than this one, and there is no set that contains a number of elements that is between this one and this one. So that's a question that we're going to consider later on towards the end of our first half on set theory. And just for fun, here's a famous unsolved problem. This is one of the problems that appears under the Millennium Problems list. So it's a bunch of very famous problems that are sort of notoriously difficult to solve because a lot of people have tried and failed to solve these problems. For every non-trivial zero of the Riemann zeta function, its real part is 1/2. The point here is not to understand what any of these words mean, but just showing you that the words for every really appear even at the highest levels of mathematics. So it's it's very important to be able to talk about these types of statements and know how to prove them. So our notation for these things is going to look like this. This upside down A will stand for all, and this backwards E will stand for there exists. An easy way to remember it is that A is like all, and E is like exists. But because we might use A and E as variables in our math, we have to somehow distinguish them. So what we'll do is that we'll flip them upside down and backwards, respectively. The structure of our statements will often look like this. We will say for all x, P holds. Now, P here is a statement about x, and it's the same thing in the existential case, about x. And this here is the exact same thing, right? We call the for all thing a universal quantifier because it applies to all x. And we call the exists symbol an existential quantifier. So a quantifier just tells you how many things your statement applies to. In the first case, you want it to apply to all of them. In the second case, you just want it to apply to at least one. It could apply to multiple, but it should apply to at least one. Okay. All right, so I think that's all I wanted to say about that. When we prove quantified statements and their negations, the plot thickens a little bit. So we'll start with for all. What we sort of should specify first is that when we say for all x, it is sort of implied that x has to come from a designated set S. You can't just say for all things, right? I want this property to hold. If the things are really unrelated to the topic at hand, then that might be a completely useless question. For example, here I started talking about these numbers, these number properties. So every natural number, there exists a number, right? But clearly these statements have nothing to do with planets or carrots. So I have to designate some special set S for which my x's are going to come from, even if I say for all x. Okay? And here I've written the bracket x just to remind you that P is a statement about x, and I'm going to call this formula 1. How do we prove a statement of the form formula 1? Well, we would have to show, given an arbitrary element in S, right, or let's call it x, we must show that P is true for x. Okay? So that's just a standard way of proving a for all statement. And it's also important to think about how we would negate this, because you know we often do proofs by contradiction. Here we go. So if statement 1 here is false, that means we can find some x in S such that P does not hold for that x. And we can write that formally as there exists an x, okay, such that P of x does not hold. And so you see here I've used the negation symbol not. I'll call this formula 2. Okay? And to really prove this, the easiest way to do it is to form a counterexample. This is a common method of proof that will be often used to prove the negation of a universal quantification. Remember, this one here is a universal quantification because it has the words for all in it. Okay. Similarly, we can talk about existence and existential quantifiers. To prove an existential statement, we have to either show that we can construct an x that satisfies the property P, and that can be very easy or very difficult, as we are going to see later. Another way of going about this is to show that if no such x existed, there would be some sort of contradiction. And so, of course, we have to again think about the negation of an existential quantifier. So how could that statement, 3 here, be false? Well, if it is not the case that there exists an x satisfying P, that means for every single x, P does not hold. Okay? So we can rewrite this using universal quantification. And notice that you have this sort of back and forth here, right? If I want to negate an existential quantifier, the result ends up becoming a universal quantifier. In my previous case, when I had a universal quantifier for all, right, it ended up being an existential quantifier when I negated it. So we'll summarize this here. When I say, here are my symbols, right? And the negation of a for all statement is an existential statement. Similarly, the negation of an existential statement is a for all statement. Okay? Here is a little warning. Okay? Unlike logical connectives, so for example, we had and, or, implies, if and only if, and so on, we cannot actually prove these two properties that I just discussed. To do so, we would have to talk more philosophically about logic, and even then there's a little bit of debate. These are just definitions and facts that makes the most sense. Okay, and also notice that I haven't given you a way of using truth tables to prove existential or universal quantified statements because it's not possible. Now, in real math, problems will often involve more than one quantifier, and when we mix them together, the interpretations that we have developed above will help a lot. So before we start though, I should probably mention that when we say things in English, we should say, like when we get the word for all x, we want to be saying for all x, this thing holds, right? And when we say there exists an x, we usually want to say there is an x such that. This such that is actually really important and will help you when you're trying to sort of parse through complicated formulas, as we will do next week. So here are some examples. Okay, so here I have a negation and then an existential quantifier followed by an universal quantifier followed by a formula. You'll also notice that from now on I'm going to be using dots. So I use dots between my quantifiers and my statements because it helps to identify what is what, and it avoids any sort of mix-up. In some books, they will not put the little dot. In some books, they'll put a vertical line. It all depends on context and who's writing. So what does this first one say? Well, it says there does not exist. So that's what the not exist means. X. And since we're talking about set theory, all of our statements will be about set theory. So they will include operations like inclusion and subset. So we will say there does not exist an X for every Y, such that for every Y, Y is in X. Okay, so let's think a little bit about what this means. There does not exist an X, okay, X is a set here, such that for every Y, Y is an X. Okay, well, for every Y means for every set, basically. Right? And here we have the statement Y is an X. So what this is basically saying is there is no set X such that every set is contained in X. Oops. And already we're starting to see the power of these universal and existential quantifiers when combined with our pre-existing logical notation. We can get such statements as this, which would be quite difficult to prove without a formal language to sort of frame them in. Okay. Here's another one. For every Y, there is an X such that it is not the case Y is an X. Okay, well, let's simplify this a little bit. So if I want to say not Y is an X, well, maybe I can rewrite that as Y is not an element of X. Okay, that would make it a little bit simpler. So this says Y is not an element of X. And so if we sort of piece this out together, we say for every Y, right, there is an X such that Y is not in X. Okay? Now, is this statement true or not? Well, that's not the focus of today's presentation, but actually this is true if you just think about the empty set. So let X be empty. So in particular, I'm talking about the set that contains no elements. Then this set clearly satisfies this statement here, because for every set, it is clear that it is not in the empty set. The empty set contains nothing. Here are two examples that show that you don't have to always say true things with your formulas. You could say false things too. So here is a statement here. There exists a y such that y is an x. And our previous example has already shown that this is not true. False. Maybe I should do it in red, actually. False. Okay. Take x equal empty set. Notice here in this statement, I haven't actually said anything about what x could be. In this case, we call x free. And the reason why we call it free is because we have not quantified over it, right? There is no quantification involving x, okay? And so the reason why this is important is because it contrasts with the previous statement where both variables were quantified over. And in this statement where it's not quantified over, there's no restriction on what x can be. So we really have to have x predefined, or else this statement does not make any sense. Okay, here's another one that is not true. For every x, for every y, right, it is either the case, now remember this symbol here means or. So either x is in y, x is equal to y, or y is inside x. Now this statement is also false, right? Because we can construct two sets, x and y. We can construct x and y such that none of these properties hold. And I'll leave it to you as an exercise to come up with such a set. Okay, here's a more mathematical example and more difficult example, which we will actually use a little bit in our program. So we're going to prove that for every rational number, again, a rational number is a fraction of the form p over q. The p and q are integers, and they must not share any common factors. So there is a linear function of the form f of x equals mx plus b, right? And the only condition I want is that it's not a flat line. So m cannot be 0, but I also want m and b to be integers, okay? Not just any real numbers. And so I want to show that I can find such a function f such that p over q is a 0 of this function. So in other words, f of this rational number p over q is equal to 0. Okay? So we can write this more formally with our symbolic notation. Again, this is not super formal because I'm still using words and I'm using these things here, functions, which I haven't actually defined in set theory. Right? And that might seem like a little triviality to you, but it's actually going to come up as a really important topic when we discuss about the Zermelo-Fraenkel axioms for set theory next week. So this is a little more formal. For every r, now r I intend to be a rational number, okay? R and q, right? There is a function, so this is a function, right? So notice now that I'm specifying where each of these variables come from. R is not a set anymore, f is not a set, r is a rational number, and f is a function, okay? And I want these properties to be true. F of x is equal to mx plus b, where m and b are integers, m is non-zero, and f of my little r is 0, okay? Now, how do we prove this? Well, remember that when we're proving a for all statement, we have to take any rational r, which I'm going to rewrite as p over q, and we're going to show that there exists such an f, okay? Now, remember that to prove existence statements, we have to either construct or show non-existence is a contradiction. Okay. In this proof, we're going to do a construction. So let's start by noticing that f of r, when f is of the form mx plus b, whenever it is equal to 0, well, that means that 0 equals to mr plus b. And I got that just by plugging in r into my statement for f of x. If I rearrange for r, well, I get minus b over m. And this actually gives us a hint as to how to proceed. Because remember, our rational function r was p over q. So if I just assign p to be equal to minus b, or m to be equal to q, then we can start from the right-hand side and sort of work backwards. So we'll set p equal to minus b and m equal to q. And so we can actually work backwards now as follows. So my number r, which is p over q, will satisfy f of x equals qx minus p, and we'll also have p over q as a 0. Okay, and since p and q were integers, because remember m and b were also integers, and q is not equal to 0, we've actually finished, right? So the existence part has been satisfied since given our rational number p over q, f of x is equal to qx minus p satisfies the conditions. Okay, and this is a sort of standard existential proof. The last thing I want to say about this is the order of quantifiers matters. So notice that when I wrote this formally, I said for all r, there exists f. If I'd switched it around, there exists f for all r, right? That's a fundamentally untrue statement, right? So if I said there exists an f, so there is an f such that for any r, right, properties, okay? That statement is false, and the reason why is because a linear function with non-zero slope has exactly one root. And so what this statement says is that I have to have a function. I'm claiming that there exists a function that has every rational as a root, and that's clearly false because linear functions have exactly one root when the slope is non-zero. Okay? That's all we are going to do for this video. In the next video, we will cover big union and intersection notation, as well as set products.